next we will look into another program that computes the LCM of two numbers, least common multiple of two numbers stored at memory addresses 6000 and 6000 hex and 6001 hex, and with the assumption that the smaller number is in 6000 hex. So, see if the numbers are say x and y. So, if the numbers are say x and y, then for finding the LCM we have to divide x by y. If I have to divide x by y and see whether this y divides x, whether y divides x or not. If y divides x, then x is the LCM. If not, we have to take the next power of x. So, x is the larger number, y is the smaller number. So, I have to take the next, so we have to take the next multiple of x. So, say 2x, and then again do the same exercise. So, I have to see whether this 2x divides 2x is divisible by y or not. If it is so, then 2x is the LCM. So, then if it is not, then I have to try with 3x. So, this way I have to just go on increasing the multiple of this x, 2x, 3x, 4x, 5x like that, and whichever multiple I have got this division without remainder. So, that is the LCM of the two numbers. So, this principle will be used for writing the LCM routine. Okay. So, we will do it like this. So, first move dptr comma hash 6000 hex. So, we have got the dptr has been loaded with 6000 hex. Now, the 6000 hex has the smaller number. So, move x a comma @dptr. So, this will be moving the smaller number into a register. Then we save this value in the register R0, move R0 comma a. So, this will save the smaller number in the R0 register. From there we move it to B register. Okay. So, we move it to B register, so that in B register the value is stored. Okay. So, then we get the next number INC dptr. To get the next number, we increment this dptr pointer and move x a comma @dptr. Okay. So, that way, so the next number, the larger number is now available in a register, and we move the larger number to R2, move R2 comma a. So, that moves the larger number to a register, R2 register. So, next we save this larger number into stack. So, we do like push 0 E0 hex. So, this will be saving a register into stack. Fine. Then we do a div AB. So, it will divide A by B. So, it will do the division, and now we have to check whether so this remainder is 0 or not. So, remainder is available in the B register. So, we move the remainder to the B register and see whether the value is 0 or not. So, CJNE R1 comma hash 0 comma some level L2. Okay. So, in L2, so if the result is 0, that means it is a the division has been successful. So, whatever was the content of A register, so that is the correct LCM value. So, that we can get back by doing this pop. So, pop 0 E0 hex, we do a pop to get the next instruction, and then SJMP over, meaning that. So, that is the end, the program has been completed. So, we have got the number. So, we do not need to do anything. otherwise I have to get the next multiple of A. Okay. So, that I can do, R 2 had a copy of A. So, we can just add A comma R 2, okay. Can do add A comma R 2 to get the next multiple of A, and then we just go jump back to this point, this push this point. So, we can say SJMP L1, where L1 is this address. So, this is our L1. This is our L1 and this is over. So, rest of anything, any other thing that you want to do. So, you can do it like this. So, in this way we can using the principle of dividing the multiples of the larger number by the smaller number, and whichever multiple divides fully without remainder. So, that is the LCM of the two numbers. So, you can use this program to get this thing. Next, we will be looking into another program. So, this program is simply in the sense that it reads an 8-bit pattern from port 1 and output it to port 2 if the number is odd, and it outputs it to port 3 if the number is even. So, this odd even check can be done by looking into the LSB of the A register, or we can just put it through a carry. So, normal strategy is like this. Whenever we have got this type of problems, so we just, if this is the register or location that we have, so it is passed through the carry. Okay. So, this LSB, so LSB goes to the carry. If you write shift by one position, LSB goes to the carry. So, we can then do check the carry bit and see whether the result is even or odd. So, that can be there. So, whether the LSB was either 0 or 1, we check that way. So, we will look into the corresponding program. So, it is like this, say this is so move A comma hash 0 FFX. So, this is required because we want to read the content from port 1. So, for that port 1 has to be configured in input mode. So, this will be doing that, move A comma 0 FFX, we will put it in the input mode. Then move A comma P0. So, when we are doing this, then the port P0 is this will be reading from port 1. So, this should not be P0, this should be P1. Okay. So, this will be P1. So, that we are reading from port 1. Port 1 is configured in read input mode. Then move no, before this I need to read the content of the port. So, this is to read an input, the port 1 has to be read. So, I am sorry. So, this should be move P1 comma A, this should be move P1 comma A. So, that port 1 is configured in the read mode, and then I can write move A comma P1. So, this will be reading the content of P1 port onto A register. So, this statement is configuring P1 in input mode. So, this is that configuration part, and this one is actually reading port P1. So, reading port P1 into A. Okay, though the statements are just similar, but they have got different meaning. Then after that I have to see whether the value read is even or odd. So, for that we do a rotate right through carry. Now, if there is a carry, that means the number was odd. So, jump on carry to label L1, and otherwise I have to, the number is even. So, for that I need to I first restore that So, this this RLC A, so this is actually restoring the carry. Okay. So, that way it is done, and then we will be move P 3 comma A. So, this is if it is if it is odd, in that case this RRC. So, here this carry bit will be set. So, it will be jumping to L1. So, if it was even, then this is moved to port P 3. So, at this point if we are here, that means the number was even. So, we rotate it left, so that the carry bit comes back to the LSB of A register, and then we move the content of A onto the port P 3. So, that it is output to the number is output to port P 3. Then after that, we can after this we can say that the whole process will start all over again. So, if it is a continuous process, so we can do it like this. So, it is I can start from this point. I can start from this point again, reading port P 1 of into A register, and this is the point L 1, and in L 1 what we do, in L 1 we rotate left carry through the A register through carry, then we move P 2 comma A, so that the output is sent to the port P 2, and then SJMP start. So, it will take us back to this point, so that it will be again continuing to scan the port P 1. If the number is even, so it will be sent to port P 2. If the number is odd, then if the number is even, then it will be sent to port P 3. If the number is odd, it will be sent to port P 2. So, that way it will this program will continue. Next, we will look into another program where so we will write a code fragment to output bit 3 of accumulator A to LSB of port 1, least significant bit of port 1, and then read the MSB of port 1 and set the LSB of accumulator to be same as the bit read. So, from port 1, so we read bit 3, so from the bit 3 of accumulator will be put on LSB of port 1, then MSB of port 1 will be put will be read, and will be set the LSB of accumulator same as the bit read. Okay. So, other bits should remain unaffected. So, we will how to do this thing. So, we can write the program like this. Say we check this bit A dot 3, and if this bit is set, then we go to the level L 1. Then we clear P 1.0, and then SJMP L 2. Okay. Then in L 1, so this is actually checking the bit number 3 of the accumulator register, and it says that if the accumulator bit number 3 is set, then I should output to LSB of port 1. So, this bit should be outputted to LSB of port 1. So, if this bit is not set, then I have done here correctly, I have outputted a 0 to LSB of port 1. If the bit is set, then I have to output a 1 at the port number port bit 1.0. So, this set bit P 1.0 is doing that. Then in L 2, I have to do the other part. So, there I do like first we try this set bit. So, this port 1.7, this MSB of port 1. Okay. So, that bit has to be read, and we have to set it to the LSB of the accumulator. So, first of all, this MSB of port 1, that should be put in the input mode. So, for that purpose, so we do set bit P 1.7. So, it is configuring that particular bit as input bit, then jump on bit P 1.7 comma L3. So, if that now this JB, so this will be reading this particular bit, and if the bit is L3, if the bit is set, then it will be jumping to L3. Otherwise, if it is not set, then I can clear the bit, the LSB of this accumulator, LSB of this register, LSB of this accumulator. So, that is done here, and then SJMP L4. So, it will be jumping to this L4, and in L3 we just we set that accumulator bit, set B A.0, and this is our L4. Okay. So, what is happening? The problem statement was that our bit 3 of port 1. So, port 1's LSB. So, port 1 0 bit. So, this bit should be checked, and accordingly this accumulator bit should be checked, and then this should be port 2, this accumulator's bit number 3 should be checked, and that should go to port 1 bit number 0. So, this part of the program is doing that. So, accumulator bit is checked. If it is 1, then it is coming to L1, it is setting port 1 this LSB of port 1. If it is not set, then it is going to if it is not set, then it is clearing that bit, port bit, and it is jumping. So, it is skipping over this portion. Okay. So, up to this much is done, and the next part of the program was to read the MSB of port 1 and set LSB of accumulator accordingly. So, the first statement. So, this configured that MSB. The next bit. So, it is next part. So, it is reading that value of port 1.7, this particular bit. If the bit is set, it is coming to this L3 where it is setting this accumulator's LSB. If the bit is not set, then it is clearing the accumulator this LSB of the accumulator. So, this way this program can be used for doing the necessary job, whatever we have asked for in the problem. So, next we will look into another example program. So, this program, so it will forcefully turn off the least significant 4 bits of port 1. So, least significant 4 bits they should be turned off. So, that is the first part, and turn on the most significant 2 bits of port 2, complement all bits of port 3 irrespective of their previous setting. So, it should not disturb the settings otherwise. So, port 1. So, the configuration should be, if this is the 8 bit. So, this lower 4 bits they should be turned off, they should be least significant 4 bits be turned off. Then the most for port 2, the most significant 4 bits will be 1, whatever be their previous setting. So, all these bits should be 1, and for port 3 all bits are complemented. So, they are all of them are complemented. So, this is the problem statement that we have. So, how to solve this in a 8051 assembly language? So, we can do it like this. So, first we say move A comma hash 0 F 0, and then AND logical A comma AND logical P1 comma A, AND logical P1 comma A. So, if we do this, what will happen with this F0, this port 1 content will be ANDed. So, port 1 was this one, and it is ANDed with F0. So, whatever was the content of port 1, so these 4 bits, so they will remain as it is in the result. So, these bits will come as it is, but this least significant 4 bits, so they will become all 0, because this is an AND operation. So, by this we can do this. Then after that I have to set this we have to turn on the most significant 2 bits of port 2. So, most significant 2 bits of port 2. So, how to do that? So, I have to set another mask for that purpose. So, we can prepare a mask like this, move 1 comma move a comma hash 1 1. So, if I write in binary, so it is easily understandable. So, this is a binary pattern. So, you can write a B at the end to tell that it is a binary pattern. So, the most significant 2 bits are to be set. So, for that the operation that I have to do is OR logical, and then with P 2 we do a logical ORing of A. So, this OR logical P 2 A, it will be ORing the content, it will be ORing this P 2 with A. So, this most significant 2 bits will get set that way. The last part is to complement the bits of this P 3 all bits of P 3. So, that you can do it like this. So, move. So, for that the mask pattern should be all 1. So, move A comma x 0 f f x, and then we XRL XOR logical P 3 with A. So, if you do XOR logical P 3 with A, so all bits are XORed. So, XORing means it will do a complementation. So, if the suppose the P 3 was the content was something like this 1 1 0 0 1 0 1 0. So, and now A register I have got 1 1 1 1 1 1 1 1. So, if you do a bitwise XORing, so this XORing will give me 1 the first bit, second bit will give me 0, third bit will give me 1, fourth bit will give me 0, fifth bit will be 1, sixth bit will be 1, seventh bit is 0, and 8th bit is also 0. So, you see that this value is just the complement of what we have previously, because the XOR operation it will always do the complementation. So, XORing with 1, so it will always give you the complement operation. So, this way we can write the program for bit manipulation, and you can do all these things by doing the using bit manipulation instructions. So, you can write this type of programs. So, next we will look into program. Next we will look into a program that will transmit continually the string hello serially at 9600 baud rate with bit data with 8 bit data and 1 stop bit. So, this is the setting. So, you see that this requires the usage of this serial transmission, and the timers are to be used. And if you remember that in 9600 baud rate, so this corresponds to this programming this TH register with the value -3. So, if you put it in the TH register -3, and then and this T mod register accordingly. So, setting those control words, we can select this -3 this 9600 baud rate for the for this transmission, for the serial transmission. So, we will do that. So, we will let us try to see how this can be done. So, first we configure this T mod register. So, move T mod comma hash 20 hex. So, what it will do? It will set this T mod register, so that you can so it is basically that auto reload and all those things, the modes and the other settings. So, that it will be operating for the this mode operation. So, it can be used for the serial transmission. And then this TH1, so it is using this timer register 1. So, TH1 will load it with hash -3. So, this way it is loading the value TH1 with -3, so that in the auto reload mode it will operate, and it will generate a baud rate of this 9600. So, that calculation we have seen previously while looking into this this timer and this serial transmission. Then the next thing to do is to set the SCON register. So, for this particular case, so you can find out that the SCON setting should be 50 hex. You remember that this SCON setting. So, this was for setting this the number of bits, 8 bit word, the 8 bit byte, then 1 stop bit. So, whatever is specified, So, 8 bit, 8 data bit, 1 stop bit and all those things, all those settings. So, they will turn out to be the SCON setting of 50 hex. Then, so we have to start the timer. So, we say set bit TR1. So, set bit TR1. So, it will start the timer. So, that now serial transmission is enabled. So, it will be able to do that. Now, what we have to do is we have to put individual characters onto this SBUF register, and those characters will be transmitted. So, what we do, first character is H for the hello, we want to transmit the string hello. Okay. So, we want to, and that we want to do continually. So, it will continually transmit the string hello. So, move a comma hash H. Okay. Then we write a subroutine send. So, which will be used to send the pattern, okay, send the string, send the character. So, a call send will do that. Then we, so H is done, next is E. So, move a comma hash E and then a call send, then H E, then L, move a comma hash L, sorry, this should be another a call send, okay. H E L, another L. So, move a comma hash L, a call send, then the H E L L O, then the O character has to be sent. So, for that we say move a comma hash O, a call send. Okay. So, over, now I have to repeat the whole thing. So, I can say SJMP L1, where in L1, so it will start doing from this point onwards again, move a comma H. Okay. Now, the send routine, we have to write the send routine. So, the send routine will be something like this. If this is that send, so it is like move. So, what in the send routine, what is required is that that the character should be moved to the SBUF register. So, move SBUF comma A. So, it is from SBUF it is doing it. Then I have to see whether the transmission is over or not. So, this TI flag, so it is raised when the transmission is over. So, I have to wait here till the TI flag is raised. Jump on not bit, transmit interrupt TI comma L2, and L2 is this one only. So, it is the program will be waiting here till this transmission is over, and then I have to clear this TI, otherwise the next character transmission it will be taken as if it has already been transmitted. Okay. So, I need to clear the TI bit from the program and then return from here. So, this way we can have a program by which some string can be transmitted over the serial lines of 8051. So, essential thing, first this timer has to be set for this baud rate selection, then the SCON register has to be set for this configuring the size of the byte, the characters or bytes that you want to transmit, and the stop bit, start bit, like that. Then this we have to start the timer at this point. Then for transmitting individual characters, the character should finally come to the SBUF register, and after doing that, after writing into SBUF, the transmission starts immediately. So, we have to wait for this transmit interrupt flag to become 1. So, till it does not become 1, the character has not yet been transmitted fully. So, we have to wait here, and once it is done, so we clear this TI bit, and then we can return. So, these are the things to be remembered.